Okay. 7.1, picking up a little bit where we left off at non-sampling error, is going to be errors that occur in the collection, recording, and tabulation of data. So that's just a human mistake. So writing something down wrong, misordering something, adding wrong, things like that. All right, so first example is we are going to take the test scores for all 10 students in the class and find the population mean. So we want to add all of those values together. Remember, mean, population mean. We're going to do the sum of our x values over the population size. So there are 10 students in the class. So let's go ahead and find the sum of those values. We're going to add, let's see here, we've got 65, 68, 70, 72, 80, 85, 88, 90, 90, and 100. So that's going to give us 808. Then we're going to do 808 divided by 10, which should give us 80.8. Okay, so that mean test score is going to be 80.8. Now let's say that's the population, so that's all 10 students in a class, but let's say I take a random sample of 5 out of that class, and I get these 5 scores, so 68, 72, 85, 90, and 100. I'm going to add all of those together. So 68 plus 72 plus 85 plus 90 plus 100. That's going to give me 415. And I'm going to divide by the sample size, which is 5. So 415 divided by 5 is going to give us 83. So the sample mean is 83. Then the sampling error is the difference between the sample mean minus the population mean. So this is the population mean. This is your sample mean. So x bar minus mu is going to give us 83 minus 80.8, which should give us 2.2. So we say 2.2 is the sampling error. It can be negative, yes. Okay, so we want to have as large as possible of a sample size to get accurate data and to reduce the sample error, because the goal is to have this number be as close to 0 as possible. Okay. So we have, when we have a sample, when it's not a population, so in chapter 6, we were dealing with populations. Now we're dealing with samples. Okay, so we have some estimators here. You have the mean of x bar, so the mean of the sample size. When we are doing sampling distributions, we are going to say that the sample mean is going to assume to be equal to the population mean. But the standard deviation will change for a sample. It will be the population standard deviation divided by the square root of the sample size. So n being the sample size. Okay, so remember, mean is, or mu is mean. Sigma, lowercase sigma, that's standard deviation of a population. And then n is sample size. Okay, now the standard deviation of the sampling distribution of x bar is also referred to as the standard error. Okay, and a theorem that we're going to use is called the central limit theorem. So we have the central limit theorem. says that with a sample size greater than or equal to 30, the sampling distribution of the sample means within a population mean and standard deviation will be normal. So what we're saying here is that as long as our sample size is at least 30, we can assume that it's a normal distribution. Okay, with a mean mu and a standard deviation sigma, regardless of the shape, even though the population distribution may be greatly skewed, okay, the sampling distribution will be approximately normal as long as the sample size is at least 30. So we want that to be, basically you're saying, okay, it's going to be valid. We could still do the calculations if it's smaller than 30, but it's not going to be statistically valid unless that sample size is at least 30. So just some examples with these calculations here. So if we have a variable, we have here, variable random x has a mean of 50 and a standard deviation of 10. Okay, for the population, calculate the mean and standard deviation of the sampling distribution when we have a given sample size. Okay, so they're going to give you the sample size. Notice in chapter 6, they never gave us a sample size. They just said mean and standard deviation. Okay, so now here they're saying, well, the sample size is 40. The mean of the sample, so mean of x bar here, that's mean of the sample, is equal to the mean of the population always. Okay, so this is still just going to be 50 for both of these. Okay, the standard deviation is what changes. Remember, the standard deviation is, so the standard deviation of x bar, standard deviation of the population over the square root of the sample size. So here we have the standard deviation is 10. So this is 10 over the square root of 40. And then we'll do that calculation and we'll round to 3 decimal places. So 10 divided by square root of 40 gives us 1.581. Okay, so there your standard deviation just went from 10 to 1. So it gets usually much smaller. Okay, but because the sample size is smaller, it's just trying to make that normal so that the curve condenses in. Remember, it's trying to get it close to this, where this is 0, -1, and 1. Okay. So then the next one, your larger sample size, will get you closer. So you have 10 divided by the square root of 55. .348. Okay, so it's getting you closer to 1. Therefore, the larger the sample size, the more accurate your data is. So we say a greater sample size greater accuracy. Okay, now z-scores. All right, in chapter 6, the z-score for a population mean is x minus the mean over the standard deviation. Okay, when we were putting that on our normal distribution curve. Now in chapter 7, you have a different one. It is x bar minus the mean of x bar over the standard deviation of x bar, which ends up being x minus the mean divided by the standard deviation of the population over the square root of the sample size. So the denominator is different. Okay, the denominator of this formula is referred to as the standard error. Okay, now you'll see some questions like this in example 1.3 because we say, okay, well, we don't want the standard error to be greater than a certain amount. So determine the sample size necessary if the standard error of 2.15 is desired when the population is known to have a mean of 95 and a standard deviation of 15. So there, we are going to do the formula backwards. So what we have is our information here. I'm looking at the formula here. Okay, so you have this formula right here. Standard deviation of x bar, standard deviation of the population over the square root of the sample size. This standard deviation of x bar, that's your standard error. Okay, so we don't want this, or we want the standard error to be 2.15. So we're going to plug that in. I'm going to do this over here a little bit so I have room to do my algebra. Okay, over, so you have standard deviation of 15 over the square root of n. So I didn't really need the mean in this case. I just want to solve for that n. Okay, so now what I'm going to want to do is I'm going to want to multiply both sides by the square root of n. They're going to cancel over here. I have the square root of n times 2.15 equals 15. I'm going to divide that 2.15 out. They're going to cancel over here. I'm going to get the square root of n equals 15 over 2.15. That's going to give me 6.977. And then I'm going to want to take that and square it to get rid of that square root. So we'll square that. Just hit that squared button. Answer squared. 48.675. Okay, but we need a sample size as a whole number. Okay, so we need it to at least be 48.675. So we're going to want to round that up to 49. Okay, so there you're going to always round up. Okay, because if you're looking for a sample size, you want at least that value. Okay, let's look at example 1.4. We have, according to Student Loan Hero, the average student loan monthly payment is $393 with a standard deviation of $75. Suppose a random sample of 100 borrowers is asked. Determine the probability that the average monthly student loan payment of the sample is less than $375. Okay, so here, this looks very similar to the questions that we had in Chapter 6. And when you're getting your problems on the test, they're not going to be sorted into Chapter 6 and Chapter 7. So you're going to have to look for, how am I doing this problem? The key here is that this sentence right here would not have been given in Chapter 6. They're not giving you a sample size. It would have just been, skip that sentence, determine the probability. Okay, so that's what you're going to look for, is things like that. Okay, they give me the sample size, which means I need to find this standard deviation right here rather than just doing the standard deviation of 75. Okay, so here what you're given is a sample size of 100. you have a mean of 393, and then you have a standard deviation of the sample would be the standard deviation of the population, 75, divided by the square root of the sample size, which is 100. So that's 75 over 10, so 7.5. Okay, and then you're going to find the probability that x is less than 375. So then we're going to find the z-score. So then the steps after that are the same. Find the z-score. 375 minus 393 over 7.5. And that's going to give us, let's see, negative 2. No, 375, sorry. 375 minus 393 over 7.5, negative 2.4. Okay, so here's my curve. Negative 2.4 is about right here. We want the probability that z is less than that, so we're going to the left. So then I would either look up that z value on my z-chart or go to my calculator, normal CDF, negative 99 for my lower limit, negative 2.4 for my upper limit. So second distribution, normal CDF, negative 99, and then upper limit negative 2.4, mean of 0, standard deviation of 1, paste. And then we get 0.008. Okay, so the probability the average monthly student loan payment is less than 375 in this sample is 0.008. So a very small percentage there, less than 1%. Okay, so that's how we're doing this type of problem. So that's a chapter 7 data. So now what you would do is compare, just kind of showing you the difference. Compare the question about population data with a chapter 7 question about sample data. So we'll do, okay, yeah, so A and B here. Just kind of going through this. Okay. The contents measured in fluid ounces of a certain brand of soda are known to be normally distributed with a mean of 20 ounces and a standard deviation of 0.15 ounces. Determine the probability that a randomly selected bottle of soda contains more than 20.07 ounces. They did not give us a sample size. So this is chapter 6. So when you're doing these problems, the first thing you're going to ask yourself is, did they give a sample size? Okay, if no, then you're going to use chapter 6 formulas. Yes, you will use the chapter 7 formulas, which is just population standard deviation, this one, standard deviation of the square root of the sample. On the formula sheet, though, they are sorted into chapter 6 and chapter 7. Okay, then step 2, we will determine all of your values here. So find mean, standard deviation, sample size if you need to, and probability. P of what are you finding? Okay, so here we have the mean is 20 ounces. The standard deviation is 0.15 ounces. We were not given a sample size. The probability that we are finding is the probability that x is more than 20.07, so greater than 20.07. Okay, then step 3, you're going to find z. Okay, so we're going to go z is x minus the mean over the standard deviation. So x is 20.07 minus 20 over 0.15. So that is going to give us 0.4667. I need to look at your homework and find out how many decimal places here, because I keep going back and forth between 3 and 4. Let's see here. Chapter 7. All right, we're doing 4 decimal places on your homework, so we're going to keep it at 4. All right, so 0.4667 for your z-score, and then you're going to plot z and find the probability. Okay, and that's your normal CDF function. So I'm going to put LL for lower limit, UL for upper limit. Okay, so 0.4667 is about pretty much about 0.5. Nope, that's on the negative side. Drew it on the wrong side. Okay, about right here. And we want the probability that it is greater than that, so we're going to go to the right. So if I were looking this up on my z-chart, I would be given this side, the area to the left. So then I would want to subtract that from 1 to find the area on the right, if I were doing this manually. But I'm using my calculator, so I'm going to go to normal CDF. And I'm going to do a lower limit of 0.4667 and an upper limit of 99. So normal CDF, lower limit 0.4667, upper limit 99. Paste. That's going to give you 0.3206. Okay, so we would follow these same 4 steps for both chapter 6 and 7 when we're doing these problems. Okay, you're just going to be doing different formulas depending on which type of problem you're given. So when we go to part B, now it says determine the probability the average contents of a random sample of 40 bottles of soda is more than 20.07 ounces. So now they're giving you the sample size. So now this is chapter 7. Okay, so we have the sample size is 40. Then we determine the mean, which was 20. And the standard deviation of x bar is the standard deviation, 0.15, divided by the square root of your sample size, 40. So 0.15 divided by the square root of 40 is going to give us 0.0237. Okay, then step 3, we find the z value, or sorry, we find the probability too. We got to do that. So p that x is greater than 20.07. Then the z. So the z-score for chapter 7 is still x bar minus the mean. It's just over the standard deviation of x bar instead of the population standard deviation. So we would do 20.07 minus 20, but this time instead of dividing by 0.15, it's by 0.0237 because we're accounting for the sample size. So 0.07 divided by 0.0237 will give us a z-score of 2.9536. Okay, which definitely changes this, but remember it's a smaller sample size, so the percentage, the probability is going to be smaller. So that's about right here. And we're going to the right. So then we would still go normal CDF. And then we would have a lower limit, 2.9536, upper limit, 99. If it's going to the left, you do negative 99. If it's going to the right, you do positive 99. So then this would be a probability of 0.0016. Okay, again, and that's this area right here. That's what that means. Okay, let's do another example. We got a couple examples and some classwork. All right. According to the NFL Players Association, the average career of a professional football player is 3.3 years with a standard deviation of 2 years. Determine the probability that the average career length of a random sample of 36 NFL players is between 2.5 and 4 years. So this is chapter 7, because they're giving us 36 NFL players. Okay, so let's find our numbers. We have a sample size, 36. You have a mean of 3.3 years. Standard deviation of the sample size is 2 divided by the square root of 36. So 0.33333. Okay, and we are finding the probability between 2.5 and 4 years, so that's going to be 2.5 less than x less than 4. X is between those two values. So we're going to find two z-scores. Okay, so for our first z-score, we'll use the 2.5. So we'll go 2.5 minus our mean, 3.3, divided by 0.3333. So let's see here. That's going to give us negative 2.4. 4002. Negative 2.4 is fine. Okay, so negative 2.4 about right here. Okay, then our second z-score is for the 4. So it's going to be 4 minus 3.3 over 0.3333. It's going to give us 2.1, positive 2.1. So about right here. And we want this area right here, so the probability in between them. Okay, so we're going to do normal CDF. And then our lower limit is negative 2.4, upper limit 2.1. So negative 2.4, upper limit 2.1. .9739. Okay, so in this sample of 36 players, you have about a 97% chance, or about 97% of them have a career between 2.5 and 4 years, because outliers is a very small amount, the ones on the outside. People who get cut in the first year or flame out, and then you got over here like the Tom Brady's. Okay, now what about 64 NFL players? So if we increase the sample size a little bit, do you think we'll have a greater percentage or a smaller percentage? I don't know. Let's find out, right? Okay. All right, so if we increase the sample size to 64, you're going to have everything the same here. So 64 for n, the mean is still 3.3. This will change the standard deviation. So the standard deviation of the population is still 2. It's just over the square root of 64. So I think that's 2/8, 1/4. So that should be 0.25. Yeah, so this is 0.25 instead of 0.3333. Then we'll do our z-scores. We want the probability that x is between 2.5, 4 years. Okay, so z-score for 2.5, 2.5 minus 4 over 0.25. That'll give us a z of negative 6. Unless I did that wrong. I did. I put 4. Sorry. It's 3.3. See, I get that really large z-score, and that's like, there might be something wrong, so keep that in mind when you're doing these. Negative 3.2, that's better. Still about right here. Okay, then 4. Okay, for this 4 right here. 4 minus 3.3 over 0.25 will give us 2.8. Okay, so now we are looking for this area right here, which means it looks like it should be greater because we're expanding that size a little bit. Okay, so then we're going to go normal CDF, negative 3.2, 2.8. We get 0.9968. So you increase that sample size to 64. Pretty much all of them, unless maybe one, would have a career length either less than 2.5 years or greater than 4 years. Okay, which sample mean do you suppose will be closer to the actual mean? Okay, we found that. The relationship, the sample size. We notice that as the sample size gets larger, okay, the mean, okay, your percentage is going to be closer to that 3.3. So we say here that x bar gets closer to mean, to mu. Okay, which means the sample mean should get closer to the population mean, because you're getting more people in the sample. Will get closer and closer as that gets larger. Okay, so now we have some classwork. Let's go ahead and, oh, it's only 10 problems. Why don't you guys do the, we could do them. There's multiple choice. Go ahead and do them. Yeah, sure. Okay, let's go ahead and go over it. So number 1, we have a population contains 14 members. The total number of samples of size 8 that you can select without replacement is what? Do you guys remember how to do this? Is this permutation or combination? Combination. It is a combination because the order does not matter. Permutation, the order matters. So then this would be 14 C8. Okay, so we would go 14 math over to probability, NCR 8. And that's going to be 3003. All right, number 2. A sampling error is what? A, B, C, or D? B. The difference between the value of a sample statistic and the value of the corresponding population parameter. An error that occurs because of human mistakes is called what? Non-sampling error. Good. All right, the mean price of all magazines published in the United States is $3.65. The mean price of a random sample of 16 magazines is $4.30. The sampling error is X bar minus the mean. X bar is 4.30. Mean is 3.65. So that was what? 65 cents. Good. Number 5. The mean of a sampling distribution of the sample mean is it's not B. It's not D. It's either A or C, right? Which one? C. It's always equal to the population mean. So it's mean sampling distribution is equal to the mean of population. All right, number 6, for a continuous random variable x, the population mean and the population standard deviation are 82 and 18. You take a simple random sample of 25 elements from this population. The mean of the sampling distribution of the sample mean is what? It's like a lot of words, right? What is it asking for? the mean of the sampling distribution. Look at number 5. The mean of the sampling distribution is always equal to the population mean. What's the population mean? 82. That's all you do there. All right, number 7. What is the formula for the standard deviation of the sampling distribution of the sample mean for sample size n, drawn from a population with a mean of mu and a standard deviation of sigma? That's just good. Yep. Standard deviation of the population divided by square root of the sample. All right, number 8. For continuous random variable x, the population mean and population standard deviation are 95 and 40. Assuming the sample size is large enough, find the standard deviation for 3 different sample sizes. Okay, so we're doing the formula in number 7, just with different denominators. So we're going to use the population standard deviation of 40. And for A, we're going to do 40 over the square root of 49. For B, we're going to do 40 over the square root of 127. And for C, we're going to do 40 over the square root of 450. Okay, so 40 over 7, square root of 49, 5.7143. For B, 40 over the square root of 127. 3.5494. And then C, 40 over the square root of 450. 1.8856. What do we notice as the sample size gets bigger? It's smaller. It's closer to 1. It's closer to that 0 and 1. All right, number 8, we have, number 9. A population has a mean of 60.5 and a standard deviation of 13.5. This here assuming n over n. So this is assuming the sample size divided by the population size is less than or equal to 0.05. That just means my sample size is big enough. That's what it's telling you. Okay, so assuming that the probability rounded to 4 decimal places that the sample mean of a sample size of 35 selected from this population is between 62.5 and 67.1. Okay, so they're giving us the sample size. So this is chapter 7. So let's identify what we're working with here. We have a sample size of 35. We have a mean 60.5. We have to find that standard deviation of x bar. So that's going to be this population standard deviation 13.5 divided by the square root of n, 35. So 13.5, I put 12. 13.5 divided by square root of 35. 2.2819. Okay, and what we want to find here is the probability that x is between 62.5 and 67.1. So let's go ahead and get our 2 z-scores. So our first z-score will be with 62.5. So 62.5 minus my mean, 60.5, divided by 2.2819. That's going to give us 0.8765. Okay, then my next z-score will be associated with the 67.1. So 67.1 minus 60.5 over 2.2819. That'll give us 2.8923. Okay, so we have our two z-scores. I'm going to go ahead and draw it out. So you have point here 0, so 0.8, probably about right here. 2.8, probably about right here. This is what we're looking for, this area right here. So we're going to go normal CDF. And then those are our lower and upper limits. So second distribution, not on there. Second distribution, normal CDF, 0.8765 and 2.8923. That's going to give us 0.1885. This area right here. Okay, so that is the probability. It's actually not telling us what this actually represents, but the probability that from the sample size of 35, the mean is between 62.5 and 67.1. Okay, and then last one. Population has a normal distribution with a mean of 51.4 and a standard deviation of 8.4. Again, assuming the sample size is large enough. Probability that the sample mean with a sample size 18 selected from this population will be more than 51.15 is what? Now, this one, the sample size is smaller than 30, but it does tell you that the sample size is large enough. It does give that caveat there, so you can still proceed. Okay. So here we would identify, so we have our sample size is 18. We have a population mean of 51.4. We're going to go ahead and find the standard deviation of x bar. So we're going to take that standard deviation 8.4 and divide by the square root of 18. That's going to give us 1.9799. And then we're going to say we're finding the probability that x is greater than 51.15. So we'll find the z-score associated with that. 51.15 minus 51.4 over this 1.9799. So negative 0.1263. And then if we put that on our chart, that's slightly to the left of 0, so maybe about right here. We want the probability it's greater than that, so we're going to go to the right. Since it's just going off to the right, our upper limit's going to be 99. So that's going to be normal CDF. Negative 0.1263, 99. There we go. And we get 0.5503. Okay, when you're doing the problems, the reason why I'm drawing them out every time is because when I look at this 0.5503, I want it to make sense. It needs to be over than 0, over the 0 there, so more than 50%. If I went to do that, like you noticed there, I accidentally, when I first typed it, 1.263. If I would have done that, it would have been like almost 90%, and then I would have been like, wait, that doesn't look right. That's why I'm drawing it out every time. So that would be a best practice for you guys, especially when you're taking a test, just because it's really easy to make a non-sampling error. And yes, that's it for class.